This is the Unit 1 Limits Review Multiple Choice Problems. So let me just run through a couple of review items here. If we want to evaluate the limit algebraically, that means your x is approaching a real number, like x approaching 3 or x approaching 0, x approaching 4 from the left. The first thing we always do is, if we see a real number, if it's a limit problem, always plug in that x value first. Sometimes there may be a one-sided limit associated with it, but we ignore that one-sided limit. We just plug in that whole number into that expression and see what we get. Now, if we get a real number value when we evaluate, then that's our answer. That's the limit. Nothing more to do there. Now, if we plug in and if we get 0 over 0, that means we have an indeterminate form. This is an incomplete form. That means that it's not undefined, but we have to continue to try and eliminate the whole so that we can reevaluate. So algebraically, what we can do is we can factor, we can go through conjugate method, we can simplify that complex fraction. And once we're able to eliminate the whole between numerator and denominator, we cancel out, we reevaluate, and we should be able to get down to our value. Now, if the result is undefined and it's a one-sided limit, then we test using decimals. So we're going to see some problems below where we have to do that. But essentially, if you get 5 over 0 as your limit and you realize that it's part of a one-sided limit, then we can say that it's undefined or limit doesn't exist because it approaches positive or negative infinity. Now, if we're trying to evaluate limits as x approaches infinity or negative infinity, then we compare degrees. If the numerator is less than the denominator, then the limit is always going to be 0. If the numerator and denominator have the same degrees, then the limit is just the ratio of the coefficients. And if the numerator is greater than the denominator, then our limit doesn't exist. Okay. L'Hopital's rule is another option for us to evaluate when we come across a 0 over 0. So if we get 0 over 0, what we can do is we can find f prime and we can find the derivative of the top and then separately find the derivative of the denominator and reevaluate. And that should bring us back to a numeric value that we can represent as a real number limit. So here's number 1. Limit as x approaches 2 of our expression. 2 is a real number, so first thing we do is we just plug 2 into our x's and see what we get. We get 2 squared minus 4, which is 0. We get 2 squared plus 4, which is 8. 0 over 8 is 0. That's a real number, so the limit does exist at x equals, the limit is 0. For number 2, limit as x approaches infinity, we see infinity, so we have to switch gears a bit. We have to compare degrees. The highest degree we see is 2. The highest degree in the denominator is also 2. They match, so we know that the ratio of the coefficients is going to be our limit. Negative 1 over 1 is negative 1. Okay, for number 3, limit as x approaches 3 from the left side of 3. First thing we do, it's a real number. I know that we see that one-sided limit. The tendency is students want to move directly into a decimal value, but we don't want to do that until we get a specific result. So let's plug 3 in first and see what we get. If we plug 3 in, we're going to ignore the one-sided limit, pretend it's not there. If I plug in 3 in for x, I get 3 minus 3, which is 0. Plug 3 into the denominator, I get 9 minus 6 minus 3, which is also 0. This is indeterminate form, which means that there is a hole that we can evaluate, that the limit will exist. So we factor the denominator, we get x minus 3 over x times x plus 1. The x minus 3 cancels out. We reevaluate the limit. Again, no decimals. So 3 plus 1 is 4. We get 1 over 4. Okay. This one-sided limit has no impact on our problem unless we get something like 10 over 0 or 8 over 0. But after we got the whole out of the way, we got 1/4. That's a real number, so that's our answer. Okay, number 4 is where we're going to run into that issue. So let's see what happens here. Again, it's a real number. We see a one-sided limit. Ignore the one-sided limit. Just plug that negative 3 in. When we plug that negative 3 in, we get negative 6 plus 1, which is negative 5. If we plug negative 3 into the denominator, we get 0. Now, negative 5 over 0 is undefined. The limit does not exist. There is a vertical asymptote at x equals negative 3. However, we don't provide our answer as doesn't exist because we look back and we see it's a one-side limit. We want to know, how is the graph moving towards that asymptote? Is it going to positive infinity or is it going to negative infinity? So to decide that without having to look at the graph, we test a decimal value in the direction that this x value is approaching. So if we're approaching negative 3 from the right side of negative 3, that x value, that decimal value is negative 2.9. Now if I plug negative 2.9 in for x, we'll see whether it's positive or negative overall. So numerator we get negative, denominator we get positive, so negative over positive is negative. So that means as we approach negative 3 from the right side of negative 3, our graph is going to go towards negative infinity. So the graph may look something like this. There's a vertical asymptote at negative 3. And as we approach negative 3 from the left side of negative 3, sorry, from the right side of negative 3, our graph is going to go down to negative infinity. Okay, let's go to the next page, number 5. The limit as x approaches infinity again. So we compare degrees, numerator and denominator, they both have the same degree of x squared. So we take the ratio of the coefficients, negative 1 over 4 is negative 1/4. For number 6, we also have approaching negative infinity, and we still compare degrees, but now the numerator has a higher degree than the denominator, which means that the limit doesn't exist. And the limit doesn't exist because this graph is either shooting up to positive infinity or negative infinity, because this value is getting larger and larger, either towards larger towards a positive number or larger towards in the negative direction. So we can test either positive or negative 100 depending on which direction we're moving in. We're moving towards negative infinity, so we can test negative 100, and that will help us decide whether our limit is positive or negative infinity. So if we plug negative 100 in for the x's, we're going to get something that is obviously negative up top. And if I plug negative 100 into the denominator, this is a much larger positive number than these other two. So negative over positive is negative, so therefore negative infinity. Number 7, we see limit as x approaches a real number. We plug 0 in, we get 0 over 0. Now 0 over 0 is indeterminate form. There's nothing that we can do much to factor this out. So we're going to rely on L'Hopital's rule. So anytime we see 0 over 0, we have L'Hopital's rule available to us, which is essentially take the derivative of the numerator and denominator separately and then reevaluate the limit. So the derivative of sine of 5x is, the derivative of sine of u is cosine of u times u prime, so cosine of 5x times 5. The derivative of x is equal to 1, so we have our reduced expression. We're going to reevaluate the limit. Cosine of 0 times 5, so cosine of 0 is 1, 1 times 5 is 5, 5 over 1 is 5, so that's our limit. For number 8, much the same thing here. We're going to plug 0 into our expression. We get 0 over 0. We're going to again rely on L'Hopital's rule. Take the derivative of the numerator. Sine of 2x becomes cosine of 2x times 2. Chain rule there. Denominator, 3x becomes 3. Reevaluate the limit. Cosine of 0 is 1. 1 times 2 is 2. 2 over 3 is 2/3. Okay, number 10. Here's our graph. We want to know whether there's a vertical or horizontal asymptote. So I'm going to go ahead and just factor this out. Numerator, I can do difference of squares, x minus 3, x plus 3. Denominator is 3 times x minus 3. I cancel out the x minus 3, so if any factors cancel out between numerator and denominator, we know that is the location of a hole, that there is a removable discontinuity. We know there is no vertical asymptote because there's no parentheses that does not cancel out in the denominator. The horizontal asymptote doesn't exist because the degree is higher in the numerator than the denominator. But there is a removable discontinuity because there's a hole at x equals 3. Right, for number 11, limit as x approaches infinity here. So let's compare degrees, but before we compare degrees, let's expand so we can actually compare apples to apples there. So if I expand the denominator, I get 4 minus x squared. Now I clearly see that my degrees match. If my degrees match, I know that there is a horizontal asymptote which exists at the ratio of the coefficients. So 2 is the coefficient of the numerator. Negative 1 is the coefficient of the denominator, so 2 over negative 1 is negative 2. Right, number 12, which statement is true about the curve? And let's start off by just factoring and see what matches and what cancels out, or if there's anything that cancels out. The only thing I can do in the numerator, I can factor a 2 out. In the denominator, I'm going to push a negative out in front. I'm going to organize this in standard form. X squared first, then the x, then the negative 2. And if I push a negative out in front, just so that I can factor with an x squared being positive, I have to change the sign of my second and third term. This factors to be 4x plus 1 times x minus 2 with a negative in front. And we see there's nothing that cancels out. And so these denominator factors are going to be the locations of vertical asymptotes. If I set 4x plus 1 equal to 0, I get x equals negative 1/4. If I set x minus 2 equal to 0, I get x equals 2. So I have two vertical asymptotes, one at negative 1/4, one at x equals 2. So that's answer choice A. There's also a horizontal asymptote of 2 over negative 4, which is negative 1/2, but that's not an answer choice. So our answer is A.